today we have Marika Swanberg from Boston University. She is a PhD student advised by Adam Smith, who's also on the call here today. And she's done a lot of great work in various aspects of privacy, and she's going to be telling us about some of her latest work on label inference attacks.
All right, thank you. Yeah, so this is work that I did during my Google research internship, and sort of since then. This was work done with Robert, Travis, Claudio, Andres, and Adam. Oh, I should also say, like, feel free to interrupt with questions. I'll try to monitor the kind of like Google chat thing, but yeah, just let me know if there are questions. All right, so kind of the overall context for this work is the fact that there's this huge push to get rid of third-party cookies to kind of avoid large-scale tracking of people across the internet. And there's been several kind of proposed alternatives for measuring advertising metrics, like, you know, click-through rate and conversion rates. Some of those include aggregation and differential privacy. And there's been lots of proposals in this space. So Google has the attribution reporting API. Meta and Mozilla have their interoperable private attribution API. And Apple has SCAN. And kind of the overall question that we had is, like, how well do these different proposals within each of these different APIs actually prevent large-scale label inference? Generally, like, what are the privacy accuracy trade-offs of all of these, and how do you compare them? Ideally, there would be sort of a unified framework of some kind. And so that requires, like, comparing these different methods. Okay, so in this sort of ad setting, we're assuming that there are sort of known features about people. And then each person also has some private label. So for example, did that person click on a particular ad? And rather than sharing this directly back with advertisers or ad techs, we would like to sort of privatize these labels using some kind of mechanism. And I'm using the word privatized here sort of to distinguish it from differential privacy necessarily. So we'll consider mechanisms that don't necessarily satisfy DP. And so, like, when we're thinking about label inference in this setting, the advertiser doesn't get to see your private label, but they do see sort of the known features about you and the privatized labels. And I'll call this is sort of like a public view, maybe not public to sort of everyone, but public to ad techs or advertisers. And so one kind of thing that makes sort of measuring label inference in this setting tricky is that if the features are informative at all about the labels, then they're correlated to the labels, right? So we have to kind of take that into account in our modeling and think about how to disentangle what can be inferred just from your features versus what can be inferred from these privatized labels, or sort of the mechanism that's being used. All right, so when we're thinking about sort of real world label inference risk, one thing we might want to do is sort of map the relationship between an adversary's prior information or prior knowledge, prior beliefs, compared to their posterior distribution or beliefs. So sort of this raises the question, like, how do we measure or model the adversary's prior in this setting? And just as a sort of example, like, if your adversary is sort of very uninformed, then they're going to make some staggering discoveries And it's not clear if that's sort of as a result of the private mechanism or just the fact that they were so uninformed to begin with. So we take sort of a fair approach, I guess. We assume that the adversary does have a fair amount of prior knowledge, and we want to measure sort of how much their beliefs change as a result of this like privatized mechanism. All right, so another sort of modeling question that we need to ask is like how to think about outliers. Certainly as a privacy researcher, I'm sort of conditioned to think sometimes only about outliers. But if we're thinking about sort of large scale inference risk or sort of like large scale tracking, we might not want to sort of frame the entire discussion just around outliers. So in this work, we consider both sort of worst case behavior and sort of more average case behavior to capture what we think is closer to kind of real world risks. All right, so we could consider like lots of ways to sort of bound this shape, this kind of like cloud of points. One are additive measures, and I'll like go into more detail into all of this. Additive measures, which are like sort of roughly bound the distance from this diagonal line. We also consider multiplicative measures, which are maybe closer to sort of like a DP style notion. And yeah, I'll go into more detail later. Okay, so in this work, broadly, we measure privacy risks and provide different ways of measuring privacy risks that allow for really an empirical comparison between different proposed privacy enhancing technologies in this like ads setting. So this requires us, modeling sort of adversarial uncertainty in this very specific setting. We also measure, privacy risk as a function of this relationship between the prior and posterior. And this allows us to adapt our metrics not only to like differentially private mechanisms, but also non-DP aggregation-based mechanisms. And one distinction that we make in our work is that we're not necessarily sort of proposing a new privacy notion, right? We're actually really just trying to measure the privacy risks. So we're not saying like, here's a new notion that you should design your mechanisms to satisfy, but rather like if you have a proposed mechanism, this is like one way to measure the privacy disclosure of that mechanism. And it's sort of more of a philosophical distinction, if anything, but I still think it's meaningful to discuss. Yeah, and then lastly, we empirically and analytically compared like label DP and aggregation-based mechanisms. All right. Oh, and I should also say, like more broadly, this work has sort of similar goals as the literature on auditing and kind of empirical privacy measurement. Here we're focused on like a very specific ad setting, and that allows us to get really detailed into like our assumptions and our metrics. But certainly like this type of goal has been explored before. All right, so there's been lots of prior work. I'm just going to kind of overview some or kind of flash some. So there's been lots of work on label DP, including like bounding worst case label inference accuracy for label DP, looking at kind of the inherent privacy and label inference trade-offs in learning settings, and also like looking at interesting mechanisms in settings where you can resample features. And then there's also been like a lot of work generally on privacy definitions that incorporate data uncertainty, sort of like we're doing. So this includes some of the kind of pre-DP sort of privacy definitions, and then also like post-DP kind of modeling as well. All right, so let's kind of return to our setting and now define more in more detail this like multiplicative advantage measure to start. So right, so if we zoom in on like one particular person, the kind of without seeing the person's label, but just seeing the person's sort of known features, I might have some kind of prior belief about what I think person two's label is. And one way to capture that is just the ratio of the conditional probability on their label. And now after the privatized labels are released, you might wonder, like, how does my belief about person two's label change? And we can capture that similarly by this kind of like ratio of conditional probabilities, where here we're conditioning both on all of the known features and the privatized labels, y tilde. And so our multiplicative measure measures really just the difference between the multiplicative difference between these two. All right, and I'll just there's just like one final transformation to make things a little easier to deal with, which is we'll just take the log of all of this. So now we're subtracting the log of these two terms. And this is actually like very similar to these kind of pre-DP metrics. I sort of didn't realize this when I was writing it down, but like it turns out other people have written this kind of metric down before. Right, so that's, oh yeah, Matthew.
Sorry, yeah, can I ask just a clarifying question? Are these privatized labels, is there like a linkage back to X2? So there will be like an X2 Y tilde 2?
That's a really good question. It depends. So if you think of like randomized response or something, then there would be like a privatized label for person two. But we'll also look at some like aggregation-based mechanisms where you'll get kind of like an aggregated privatized label.
Okay, that's
yeah.
helpful. Thank you.
Yeah, I was sort of purposely vague about that for that reason.
Makes sense. Thanks.
Are there any other questions? Just this is a good stopping point. So, all right, cool. Okay, so this is our multiplicative advantage measure. And this is sort of like a visual depiction of what it looks like. If we look at the adversaries, can you see my cursor actually? Is that visible? Okay. If we look at the adversaries' prior belief as a function of, or like rather their posterior as a function of their prior, this limits sort of the multiplicative difference between these two, or rather sort of their change in confidence. And if your mechanism is labeled DP, then the slope of this line corresponds to like e to the plus or minus epsilon. Okay, so right, so one sort of observation you could make is that if M is epsilon labeled DP, then no matter what your data distribution is, or what the data features are, or the mechanism output, the multiplicative advantage will be bounded by plus or minus epsilon. So this sort of translates a sort of a worst case label DP guarantee into something about how much an adversary's belief is updated. Okay. Oh, yeah, Dover? Oh, sorry.
So just to be clear, you're assuming the labels here are 0 or 1. How would this metric look if you had a larger label class?
Oh, good question. So, yeah, I think you could, let's see. So I think you can formulate this generally for like any pair of labels. That's my
So
sense.
you take a max over all pairs of labels or something like that.
Yeah. Yeah,
Okay.
you could have like um the ratio of the probability that y equals a over yi equals b or something. That's sort of my very initial reaction to your question, but I would have to think about it in more detail. Okay. All right. So right. So we talked about label DP. That's a very natural kind of notion that you might use to protect the privacy of the labels. Another mechanism that's been proposed is something called learning from label proportions. So in this setting, you have, again, public features. And rather than getting sort of a noisy label for each person, um, instead, the whole data set is randomly partitioned into bags of a particular size. So in this case, the size is 3. And for each bag, you're given the feature vectors for all the people in the bag and the proportion of ones, for example, in the bag. And yeah, so that's like another proposal. It's clearly not like differentially private, but if your bags are large enough, we sort of think that we might get some measurable privacy guarantees. All right, so when we apply this metric to LLP, there's sort of some assumptions that we need to make. So in particular, for worst case bag, the multiplicative advantage might be infinite. And in particular, this multiplicative advantage is the ratio of 2 Poisson binomials, which are sort of like regular binomials, but you're flipping a bunch of coins that have different biases. So it's kind of a generalization of that. So we know what the distribution is, and sometimes it's unbounded. And there's sort of 2 reasons that could happen. One is that all of the labels in the bag are the same. I'll call this a homogeneous bag. So if I know that none of the labels are ones, for example, then I definitely know everyone's label. And the other type of bad event is when everyone's labels are deterministic, but maybe person I's label isn't. So that's when you can get kind of an unbounded multiplicative advantage. All right, so we think sort of the second one is less of a concern for real learning settings where there's some uncertainty about people's labels, especially in the ad setting. It seems like there should be some amount of randomness. But this first type of event, we are sort of worried about. So we can sort of think of this as a system failure, and we need to choose large enough bags so that this just won't happen very frequently, if at all, on the entire data set. And that's something that I'll talk about in our experimental section. So to kind of get around this, like we sort of, if we take a worst case approach to LLP, then basically that's just going to say you don't get any privacy. So instead, we're going to take sort of an expected case approach using uncertainty from the fact that the sort of assuming that examples within a bag are drawn IID from some distribution. And with uncertainty about person I's label. So you can imagine sort of after seeing the public features and the privatized labels, like these label proportions, you can imagine sampling from this conditional distribution and sort of kind of considering uncertainty about personized label from that. And these assumptions are like plausible. Sort of for assumption 1, the bags are randomly assigned in our mechanism. They're not totally IID because we're sort of sampling without replacement, but it's sort of like pretty close to an IID setting. And for the second assumption, we think it's reasonable because in this setting, we're not really thinking that there's like a true label for each person. Like there isn't like a some truth to whether you would click on an ad or not. And so there's sort of some inherent randomness in the labeling process. And we'll also need to assume that like sort of during, while measuring these privacy risks, that you actually know this conditional distribution. All right, so I'm going to talk about our empirical setup where there, oh yeah, Charlie?
Yeah, I was wondering if you guys also studied this like bagging technique with privacy applied to like privatize the label proportions, or like if not, like why not? Like, or are you interested in something that's like gonna give better utility, or like, yeah, just interested in your thoughts on that.
Yeah, that's a really good question. We have done some like preliminary experiments on that, but we haven't like really done a deep dive into like what happens when you do aggregation and DP. But it's certainly like something that's worth looking into because that's also like a really natural mechanism for protecting privacy in this setting.
Thanks.
Okay, so yeah, so we did some experiments on this. I'm not going to talk about all the experiments we ran, but just a subset. So we considered, well, several data sets, but 2 of them that we considered were this KDD12 click-through data set and Higgs. And for these, because we didn't generate this data, we don't actually know the conditional distribution over the data. So what we do is, in order to measure the multiplicative advantage, we sort of estimate this conditional probability by training a calibrated model non-privately on a subset of the data to then get a sense for what the actual conditional probability is. And then we use that to measure multiplicative advantage empirically. And we also used a synthetic data set where we did just sample this conditional probability from a known distribution. And in that case, we can compute the multiplicative advantage more or less exactly. All right. So, so here's one set of experiments. Here's our synthetic data set where we've considered LLP with different bag sizes. So K here is the size of the bags. P infinity is the probability of seeing a infinite multiplicative advantage. And then here, like we've also plotted the analytical bounds for randomized response, are really like any epsilon DP mechanism. So here, like you can think of epsilon as corresponding to an upper bound on the multiplicative advantage on this axis. And yeah, like generally what we see on this for data that's distributed like this is that as you increase the bag size, the probability of seeing an infinite bag or like a homogeneous bag goes way down, as you would expect. And here's another example. This is Higgs. So we first had to train a classifier to sort of learn the conditional distribution over features and labels. And then we measured the multiplicative advantage from that. And we see a similar sort of trend, like, P infinity goes way down as you increase bag size. And generally, like, the multiplicative advantages concentrate towards 0 as you increase that bag size. And so that's like one of the main takeaways, sort of like what you would intuitively expect. If you're aggregating over lots of people, then there's sort of like a lot less information that's being revealed. And also, like, once P infinity becomes, negligible, we could potentially compare sort of the protection that you get from LLP to like different epsilons. So like maybe for bag size of, I don't know, like 32, you can compare that to epsilon of 1/2 or something. And this sort of one thing that makes this, oh yeah, Charlie.
Oh, you can finish your thought.
Oh, okay. One thing that sort of complicates this is the fact that this is the advantage on one bag, but if you have like thousands of bags, you would want to consider the risk of seeing one of these sort of bad bags over the whole data set. So you would take some kind of union bound to make sure that you're just probably never going to see an infinite bag. Yeah. What was your question?
Sorry, I have to run in just a minute, but I was wondering if this like how this metric handles something like composition, like if we wanted to measure the bags multiple times, do we have something similar to DP where we have something that's like nicely additive, or do things break down?
Yeah, that's a really good question. In general, like in the worst case, things could completely break because, if you have two bags that overlap or sort of differ by one person, then you could potentially infer a lot. But yeah, so we don't really study composition at all. I think, at least personally, my sense is that there's sort of like so much data that would be aggregated in potentially different ways that it's kind of all lost in the wash. Mm-hmm. But other people can chime in too, like my collaborators might have other opinions.
Thanks, Marika.
Certainly with epsilon DP, of course, you would get composition. So, yeah. Adam, you want to chime in?
Yeah, I was just going to say, I don't think these measures say much about composition, as you said, Marika, and so I think at best one should view these as applied holistically to the kind of final thing you're doing, as opposed to indications of how well things would compose.
Mm-hmm.
Got it. Yeah, that makes sense.
Unless you have some additional like assumptions, or unless you know more about the system. I guess in some cases you might be able to say more, but like it would require extra information.
Yeah, I think like especially in the setup of like ads measurement, like I think like understanding like composition and like something like group privacy is like useful, because we're in this kind of continual release setting where like the data keeps coming in and the privacy loss keeps growing over time, because unless we just like turn the APIs off at some point in the future. So like understanding how the privacy loss grows over time, I think is important. And I think that's kind of where my question about composition is like coming from. But anyways, I have to run, but thank you so much for this presentation. It's like really great.
Yeah. Thank you for your questions. All right. So yeah, okay. So another data set that we looked at is KDD12, this click-through data set, which is notoriously skewed. Almost no one clicks, which sort of like also comes up in the ad setting. And what we see here is sort of like not really the same trend with the probability of homogeneous bags going down a lot. So even for sort of pretty large bags, we see that you have a really sort of high rate of seeing homogeneous bags. I'll talk about that at the end, but sort of just as a preview, like at least in the click-through setting, it seems like this might not be a problem depending on how you look at it, because sort of these homogeneous bags are bags of zeros, people who didn't click. And so maybe that's not as much of a privacy violation, but I'll talk about that a little more later. All right, so I'm just going to briefly talk about our additive advantage measure. So this captures sort of a different notion of how much the adversary's belief changes. And yeah, just kind of sort of a different way of measuring this difference. Okay, so we'll start by considering our sort of baseline uninformed attacker, and we'll measure, we measure the base error of that attacker. So it's kind of like, what's the best label they could predict given your features, and then subtracting that from sort of the optimal informed adversary, so one who can condition on both the features and the mechanism output. And here, sort of like I mentioned, because we're looking at expected additive measure, additive advantage, we're going to take the expectation over sampling the features, sampling the labels from this conditional distribution. And so the reason I wanted to talk about this isn't necessarily for the measure itself, but because we actually, for this, we have experiments showing the privacy and accuracy trade-off in terms of the additive advantage. So here, again, for KDD12, we've plotted the expected advantage for different mechanisms. So here, like, we consider randomized response with various epsilons and LLP with different bag sizes. And so we've plotted the expected advantage and then the AUC of sort of the best model we could train on using these parameters. And like for each of these points, we did some parameter tuning to get sort of the best learning rate and batch size and other parameters. And so like overall, we see that like this privacy and accuracy trade-off is pretty similar for these two mechanisms. And we did the same thing for Higgs and see sort of a similar trend. There is like some difference between these, but overall kind of, it seems like they have similar privacy and accuracy trade-offs. And we sort of think there's maybe a fundamental reason for this. I'll kind of paint a broad picture of why we sort of think there's kind of maybe a fundamental privacy accuracy trade-off, but like in very broad strokes, we sort of think that 1 over square root of k behaves sort of like epsilon. And this is for sufficiently balanced data sets. When the data sets are really unbalanced, weird things can happen. So in terms of privacy, we found that for LLP with a bag size of k, the multiplicative advantage is only bigger than 1 over square root of k with like probability delta. And here, like, I've sort of hidden factors of delta in this part of the term, but sort of morally, you can think of this as epsilon. There's like caveats to this statement, but sort of in broad strokes, we can think of 1 over square root of k as being similar to epsilon. And then in terms of accuracy, prior work studying LLP showed that LLP requires roughly like k times more input points to get the same accuracy that you would get on training on like event level data. And the same kind of trend holds for learning with label DP. So you need roughly like 1 over epsilon squared times more input points. So sort of like very broadly, both in terms of privacy and accuracy, it seems like epsilon behaves similarly to 1 over square root of k, but again, this is sort of very broad, like kind of take this all with a grain of salt, but there might be kind of an underlying reason for this similarity. All right, so just to kind of wrap up, you know, we come up with sort of new ways of measuring privacy risks that allow us to empirically evaluate different proposed privacy enhancing technologies in this ad setting. We sort of model adversarial uncertainty in this setting sort of explicitly, and sort of measure privacy risks as a function of the relationship between prior and posterior. And then this allows us to compare privacy and accuracy trade-offs for DP and aggregation-based mechanisms. And I should say, like, for those of you who are like at Google, there's production code for this that I worked on for training JAX models with LLP and DP. So if you want to experiment with that, you can. And there's also, Travis has a TensorFlow implementation. So yeah. All right, so this work has raised a lot of questions for us. I'll just talk about some of them kind of more narrowly. Like, it raised some modeling questions, especially in the ad setting, where there's sort of an asymmetry about like the privacy of different labels. Like the fact that someone didn't click on an ad sort of doesn't seem as revealing as the fact that they did click on an ad. And you know, you can disagree with this, but for example, someone might have just had an ad blocker on or just not even seen the ad. So it sort of doesn't give as much signal about someone's preferences. And so if we sort of exclude that kind of bad case, then homogeneous bags of all clicks become really improbable and might capture kind of this setting a little bit better. There's also sort of, this came up already, but there's natural DP mechanisms that we haven't measured yet. So we're still kind of looking into how doing like aggregation plus DP kind of compares to all of these other proposals. All right, and then sort of more broadly, like, you know, you might wonder, like, when are these adversarial assumptions that we make warranted? Like, I actually personally have no idea what risks models companies have in mind, but it's worth thinking about kind of the adversary that they're imagining and sort of what the risk tolerance is within that setting. We also, like, sort of in discussions talked about, like, maybe sort of the point of these privatization mechanisms is to deter large-scale reconstruction, and maybe like kind of deterrence is enough, or maybe you could consider like the cost of large-scale reconstruction and take that into account. And also, I should just say, like, from what I've learned, like the ad setting is much more complicated than our modeling. Like, and so it's sort of not clear, even if kind of like what the right way to think about threats in this setting is. And sort of, we're very focused on like particular proposals, but, you know, maybe that's sort of too narrow. There's certainly like lots of other ways to think about privacy risks in this setting. And sort of like, lastly, this has kind of been on my mind lately, like, if my label is inferred, like, do I really care if it came from correlations to public features or the private mechanism, right? Like, sort of the effect and the harm is the same. So, and here, like in our modeling, we sort of assumed that it's okay to learn correlations, but we want to prevent sort of inferences from the private mechanisms. But kind of like to an end user, they're sort of the same. So kind of just thinking about that in more detail, I think would be fruitful. But yeah, that's all I had. Thanks for listening. Also, I'm on the job market, so talk to me if you have headcount.